Alrighty, so let's get started with week 13. And week 13 is one of the last pieces of the puzzle, and we talk about graphs. Okay, so what is a graph? I guess maybe I should, let me just jump to my other class so you can see some different kinds of graphs. I should post that in here too. I will. Graphs. Okay. All right. So graphs are what you have in math pretty much. Okay. There's different kinds of graphs, and they're used for different purposes. So this is one example of a graph in here, and it's basically kind of sort of like a tree, but that does not really follow the orders of a tree in the sense that we have nodes and we have connections to these different nodes or edges. But unlike the binary tree, each node does not have only one unique path from the root, and each parent doesn't have just two children. You know, you can have multiple connections from node to node. So these are used sometimes to simulate something that's on a map, like if you have a bunch of cities and you're trying to figure out what's the fastest way to go from one city to another city. Another application for a graph is, just the graphs that we have in math, right? You have the x-axis, the y-axis. That will be another example of a graph. You could have weighted graphs. Weighted graphs basically mean that the paths or the connections between the different nodes, they themselves have values, right? So if you're going from this city to this other city, if you're going from Albuquerque to San Francisco, that's 900 miles or whatever. If you're going from San Francisco to New York, that's 2,600. So the actual path that you travel has its own specific value on top of the actual edges, which have nodes, which also have values. You could also have a directed graph, which means that you actually can have a direction going from one location to another location, and you can add more on top of these. You can have a directed and weighted graph at the same time. That's also possible. So these are the kind of things that that are possible with graphs. And let's look at what I have. So for week 13, what I have in here is basically just go to chapter 13 and read the Lafore book. Okay, so what does Lafore say about graphs? Well, a few things. So I already showed you what a graph is and for what they're used. So we have a way to measure adjacency, whether one thing is close to another one versus not close to another one. So there's a ways for us to mark these. We have paths, and there's some examples in here of what, here's your real world map, right, of where in somewhere in San Jose, right, and how we could simulate something like this on a computer science graph. Okay, you have connected versus not connected graph, right? So this one on the left, everything is connected. The one on the left, you have different pieces that are part of the graph that are not necessarily connected with each other. I already showed you what is a weighted graph, what is a directed graph. Okay, one of the first people to come up with this idea in mathematics was Euler, right? And Euler methods, I think that's part of differential equations. Don't hold me to that. But there's the problem that he tried to solve was there was a bunch of bridges in some city, and he was trying to find a unique path through which you can cross all these different bridges without repeating. And he had to come up with some kind of a mathematical model for that. And it turns out at the end that you can't really do that kind of thing, given these particular this particular problem. So how does this apply in computer science? Well, every vertex is basically what we used to have as a node, right? So instead of a node, we're calling it a vertex now. and it has its own unique value. It could be some kind of a character to label this thing, and it also has a Boolean to mark the thing that it has been visited or it hasn't been visited, in case we want to travel from one path to another one. Okay. There's different ways to represent a graph. One way is to represent it using arrays. Another way to represent it is using an array. Okay. And one convenient way to do this is to create a two-dimensional array and make an adjacency matrix, right? So for example, where's the picture that I have? No, I don't have it. 13.1, where's the actual picture of the vertices? I think, no, that's not it. Wait. So this is adjacency matrix for 13.2a. Where's 13.2a? That would have been nice if I 13.2a. I know it was there somewhere. 13.2 3 2a. Okay, all right. So we're looking at part A, right? So the adjacency matrix is going to show us how each of these different ones are connected to each other. So let me just do this. I'm going to take a picture of this. All right, that's my graph. Pull that picture in there. And let's look at my adjacency matrix. All right. So have a look at this thing. So the A is connected, is adjacent to B, which is and A is also adjacent to D, and A is adjacent to C. And in the matrix, we're going to, which is basically a 2D array or just like a spreadsheet, we're going to put a 1 if there's an adjacency between the different vertices, and we're going to put a 0 if there isn't an adjacency. Right? So for example, A is adjacent to B, C, and D. That's why we have zeros here. A is not adjacent to itself, so we put a 0. B itself is adjacent to A and D, which is where we have these two zeros, and you have, two ones, and the two zeros are B and C, which is basically what B is not adjacent to. C is only adjacent to A, so that's the only one that we have. D is adjacent to A and B, and those are the ones that we have in here. So that's the adjacency matrix. And the way we're going to do the adjacency matrix is basically just a spreadsheet, right? You have rows, you have columns, and you put zeros and ones to indicate what was adjacent to what. That was one implementation. Another way to implement this is to create linked lists to indicate what's adjacent to what. In this table 3.2 here, you can see that A is adjacent to B and C and D. Don't confuse this linked list as the path that this must follow, right? It simply says that, the only things that are adjacent to A are the B and the C and the D, not in any particular order. The only thing that's adjacent to B is the A and the D, etc., etc. And the implementation that the book takes is to use the 2D array, not linked list. Okay. So the way you're going to create this adjacency matrix is, let's say, for example, the element the element identified as 1, 3. Suppose that element in the table is adjacent to another element, which is the 3, 1. The way we're going to indicate that both of these are adjacent is we're going to put ones next to each of these. Okay, so the actual graph class uses one array for the vertices itself, and it uses a 2D array for the integers of the adjacency. So this is your adjacency matrix, a 2D array, and the actual vertices is a one-dimensional array. Okay, and again, you can give it a size initially, all that good stuff. And you have a constructor which basically makes the whole thing equal to 0, right? All the adjacencies are set to 0 initially, and ways to display these different vertices if we wanted to show the labels. Okay, so two of the most important things that are part of these graphs are the searches that we can do in graphs, and those are DepthFirst Search and BreadthFirst Search, so DFS and BFS. Okay, and there's different applications. You already saw the one with the bridges and the one with the map, right? Another very popular use for maps, for graphs, is when you have the internet, right? The internet is just a series of routers. Routers are all have a way to connect to each other or exchange the information about how fast packets traveled to get to a certain place from a certain place, and the routers keep tables in them to keep track of what's the fastest way. Maybe if some router is down, you have that in the table as well. So the way you're going to determine how to get from one place to another place is using graphs. Okay, and it also has applications in like electrical engineering and circuit boards and stuff like that. So first of all, the DepthFirst Search algorithm. Okay, so the DepthFirst Search algorithm, you're going to start at your origin or wherever you're starting, and you're going to try to break as far away from it as you possibly can before you go and visit the next vertex that is connected to the origin, right? A good example or an analogy to have for this is if you are in some kind of a maze, right, and you're trying to figure out your way out of it, right? So what you're going to do is, suppose you have some kind of a string attached to you, right? So you're going to tie that string at A, right, and then you're going to try to go to B. And if B has multiple different ways where you can go from it, you're not going to go, in every possible direction. Well, you would try to go in every possible direction, but first you're going to try to explore the path from one of these routes all the way until you get to the end, right? So you basically you connect the string to A, then you go to B, then you're going to go to, from B, you're going to try to go to the next one, to the F, then you're going to go to the H, and at that point you dead end it, and now you're going to start following the string back to where you came from. So you're going to go back to F, you're going to go back to B, you're going to go back to A, and that's pretty much, now you started exactly where you ended where you started, and then you get your string and you start going back to the C, right? When you get to the C, that's a dead end. You follow your string back. Then you go to the next path that is connected to the A, which is the D, right? Follow the string down all the way to the 8, right? That's the dead end. Then you follow the string back to the A, and then examine the last possible path, which is the E, right? And that's pretty much how the DepthFirst Search works. Okay, so that's that, and the way. What's that? Yeah, you go A. It can. You can tell it. You can tell it to start at AE and then go to DGI, right? Yeah, it doesn't. It doesn't really matter. Yeah, as long as you start down one path and you keep going until you hit the dead end, and then you go back to where you started. So that's the DepthFirst Search. You're trying to get away as far as possible from where you started until you hit the dead end, and then you go back. Okay? And the way we're going to implement this algorithm is as follows. So if it is possible, you're going to visit an adjacent unvisited vertex. And remember that each vertex has its own Boolean stored in it to indicate whether that thing was visited or not. So if it is unvisited or the Boolean is false, go to it, and then you go to the next one that's connected to it. And what you're going to do is, as you mark each vertex as visited, you're going to push it on the stack. And conveniently, we're going to be using the same exact stacks that we already created in this class. Okay, so you're literally pushing on the stack that you have already created in the previous chapters. So you get to a vertex, mark it, push it on the stack. Okay, and then if you cannot follow rule 1, right, then what you're going to do is then you're going to start popping things off the stack. Okay, and if you cannot follow the rule 1 or the rule 2, then you're pretty much done. right? So if I go in there and I grab my little picture that I have in here, let me copy it so you can see it. And I'm going to go to my little table that I have in here, which is in the book, which you should have. All right, so this is my picture. All right, so what we're going to do is we're visiting A, we're visiting B, we're visiting F, we're visiting H, and all of these are being pushed on the stack, right? When we get to the dead end, right? When we get to the dead end at H, right, we start popping things, right? So we pop the H to go back to the B, we pop the B to get back to the, we pop the F to get back to the B, we pop the B to get back to the A, and now that we got back to the A, we have already marked B as visited, right? So we can't go this way anymore. So now we're going to go some other path that, it hasn't been visited, and it makes sense to go to the C, right? So once we visit the C, we're going to push that on the stack, and try to move this thing. All right, and then once we get to the dead end of C, then we start popping it. We pop the C to go back to the A. We're back to the A, and then we have already visited the B and the C. We're going to go the next path down the next path, which starts with the D. So we're going to push the D on the stack. Then we're going to push the G on the stack. Then we're going to push the I on the stack. When we get to the I, that's a dead end. When we pop the I, pop the G, pop the D, we end up at the A. We already visited the B, C, and D, so the only place left is the E. So now we're going to go and push the E on the stack, and once we pop the E off the stack, then you're pretty much done, right? You get to the A, and there's nothing else. There's no other place to visit, and that's it. So that is the DepthFirst Search algorithm, okay? And if you look at the code that the book has for this, you're going to see that it marks these as 1 when they're visited, and the mark is where is this thing? Peak. If it's visited, else. Okay, here you go. Here it is. Here's how it marks it as visited. Okay, so if the stack has not been visited, you mark it as true, and you display the vertex and you push it on the stack that you have. Okay, so that's pretty much how it works. Okay, and you have the whole DepthFirst Search program in there. I highly encourage you to type it up and get it working. Similarly to how we had to do the little diagrams for the linked lists and for the trees, it will really help your understanding if you get the code and trace it line by line to see visually how things are getting moved onto the stack from the code that you have already written. And again, you already know what the stack is. It's the same exact stack that we have written, so that's nothing new. The only thing new this time is we're creating a class vertex, which is not a very fancy thing to do. And then what we're doing is you already have your graph constructor to initialize all the vertices as unmarked so that you can visit them. Okay, and anytime you're adding an edge, we're going to create an edge which is 1, 1 to indicate the adjacencies of these different edges. Okay. So that's the DepthFirst Search. And other than the DepthFirst Search, there is, and by the way, DepthFirst Search is useful in kind of in game simulations. So if you have some kind of a game, you take the outcome of one turn can generate multiple possible outcomes of another turn. For that turn, you have to follow down these outcomes to get to the possible final outcome. So that will be an example of a DepthFirst Search. The other possible algorithm to search through a graph is the BreadthFirst Search. Okay, and by the way, these two, the DepthFirst Search and BreadthFirst Search, are some of the some of the questions that really do pop up quite a bit in these job interviews, right? So I would highly recommend to see how the book implements it here. And the book doesn't even use recursion or anything like that, but there's ways for us to implement these algorithms recursively as well. So the BreadthFirst Search is similar to the DepthFirst Search, except instead of a stack, what we're going to use is we're going to use a queue. Okay? And the rules for visiting this, for doing the BreadthFirst Search are: you're going to visit the next unvisited vertex, if there's one, that's adjacent to the current vertex. You're going to mark it, and you're going to insert it into a queue. Okay? And if you cannot carry rule 1 because there are no more unvisited vertices, remove that vertex from the queue and make it the current vertex. Okay? So the way it's going to work is you're going to start at A, you're going to go to B, you're going to go to C, you're going to go to D, you're going to go to E. And then once you have gone as far as you can, right? Then you're going to go to the next one down. You're going to go to the F. Then from F you're going to go to the G. Then from the G you're going to go to the H. And then from the H you're going to go to the I. Okay, so if the DepthFirst Search, you try to break as far away from the root or the origin as you possibly can, in the BreadthFirst Search, you try to cover all of these different nodes or vertices that are near the origin before you move one down. Okay? And there is a queue basically in here so that you can see how that works out. Okay? And how we're going to be removing these. So first, we have, let me get the picture. So I'm going to get this. This is my BreadthFirst Search, and if you need pictures and you want me to draw diagrams for this, I'll be happy to. So let's look at how this works out. All right, so we're going to visit the A, then we're going to visit the B. We're going to and this is what happens with the queue, right? So we're visiting the B. Adding it to the queue. We're visiting the C, we're adding it to the queue. We're visiting the D, we're adding to the queue. We're visiting the E, we're adding to the queue. There's nothing else to visit, right? So now what we're going to do is we're going to remove B from the queue. We're left with the C, D, E, right? Then we're going to go to the F, right? We're going to add that to the queue, and from the F, the next thing we're going to do is we're going to remove the C, we're going to remove the D, then we're going to go visit the G, right? And we're going to keep removing and removing and removing from the queue until it's all empty, and then it's done. Okay? So it will really make a lot more sense to trace the code as we've been doing with the trees and and the linked lists in order for you to visualize this. Then because this just right here is probably not going to be enough. But I highly encourage you to do these graphs by yourself, because just looking at my graphs, I don't think is enough. You have to do it yourself. Okay, and that's pretty much what I wanted to tell you about graphs. So the main things are DFS, the DepthFirst Search, and the BreadthFirst Search algorithms, and both of them are implemented in the book. And you can see the code in there for both of them. The code is not super complicated, but again, you would have to. In order to benefit from this, you should trace it line by line, just like we've been doing so far. And I'll be happy to show you some more details if you need them. Okay. So that's all I want to tell you about graphs. Any questions? Queue?
The queue for the BFS. Is this the regular queue?
The queue is for the just the regular queue. Yeah. You come from one side and you remove from the other side. Yeah. Yep. And the nice thing is that if you have done the queue and the stack already, you're going to recognize your code in there. There's your queue, right? The same exact queue that we did. You know, actually even simplified, because we at some point we had to do a double-ended, you know, queue. So you don't have to do that. It's not even a priority queue or anything like that. Okay. So that is what I wanted to tell you about graphs. And if you want me to draw some more, you know, diagrams for you, let me know. I'll be happy to do it. Alrighty. So I'll post the video for you. Send me your emails if you have any. Just come see me in the office.